Hello! In this lab report, I will be discussing the properties and analysis of oscillating motion. The purpose of this study was to observe the motion of an object that is acted upon by forces caused by a spring and gravity. The motion of the object was provided as a video, then it was analyzed using the program tracker. Its movement in the x and y directions, as well as the energies that were present, will be compared to the predicted motion using a computational model. The object that was analyzed for this project was a load hanging by a spring. This is the video that displays the motion of the load. As the spring is pulled away from its rest position, the load oscillates in both the x and y positions. Then, the motion of the object will be analyzed frame by frame in the program tracker. It will propagate motion graphs for the x and y positions and a table showing the position of the load at each interval in time. The table shown here has been pasted into Microsoft Excel so that it can be used in the computational model. To describe the predicted motion, we first need to address the net force in this model. The only two forces that are present are the force of gravity, which always points in the negative y direction, and the spring force, which changes direction based on the position of the load. Similar to previous labs, we are using the momentum principle, which sets the net force equal to the change in momentum, to update the position and velocity at many intervals in time throughout the object's motion. Before the code is updated, we first need to find several values to describe the object's motion. The first value that we need to calculate is the spring constant. To do this, we'll start by finding the period of oscillation from the motion graph in Tracker. I subtracted the time at the left arrow from the time at the right arrow, then divided by 4 to find the average period. Then I took the equation for the period of oscillation and rearranged it to solve for k, which is the spring constant. After plugging in the mass of the object and the period, the spring constant was calculated to be 6.87 newtons per meter. The other value that is necessary to create a computational model is the length of the relaxed spring, or L0. When the spring is in its relaxed state, the force of gravity is equal to the force of the spring. Setting these two formulas equal to one another allowed me to solve for L0, which is 0.127 meters. To create the predicted model of the object's motion, a GlowScript program was edited with the initial values used in the video. The mass of the object, initial position, and initial velocity that were found using Tracker were inputted as values into the code. The spring constant and L0 that were previously calculated were defined as shown. In addition, the variables L, L hat, and S were set using the spring formula. The values for gravitational, kinetic, and spring potential energy were defined, as well as the formula for the total energy. Next, the initial states for the energies at each time step were defined in lines 108 through 111. The formulas for the gravitational, spring potential, and net force were included to calculate the initial values of each. Then, using the momentum principle, the force, then velocity, and therefore position can be updated for each time step. As the program runs, you can see that the motion of the ball in the model moves similarly to the motion of the load in the video. The computational model of the object closely mimics the position values at the intervals of the tracker video. The following graphs show the motion of the computational model compared to the actual tracker position values. You can see that the prediction motion is very similar to the actual motion in both the x and y directions. The energy graph shows the changes in gravitational, kinetic, spring potential, and total energies throughout the time that the data was recorded. As the object begins to move, gravitational and spring forces are converted to kinetic energy and back to potential energy. You can see that the changes in all three forces are oscillating, but they always add up to 0. This means that there is no change in the total energy of the system, and it stays constant throughout the entire time. Now it's time to talk about the energy principle in this experiment. The energy principle states that work is equal to the change in energy present in a system. Because there are no forces acting on our system from the surroundings, there is no change in energy throughout the motion of the object. This is shown in the energy graph that was generated in GlowScript. There is no change in energy. Lastly, we need to discuss the periods of oscillation in this experiment. There are actually two different periods of oscillation, one in the x direction and one in the y direction. You can use either graph to calculate the period, but you will get a different result. These two calculations from the tracker motion graphs show that the period for the x direction is 1.64 seconds, while the one for the y direction is 1.52 seconds. This lab allowed us to explore the motion and energies involved in oscillating motion, and we successfully modeled the movement of an object using GlowScript. Thanks for watching!